Ah. Oh, okay, gotta start. I gotta start. Gotta start school. Okay, let's go. Let's go. Properly seated. Okay, okay, folks. Let's get some music going here. Okay. All right. Hello, students, and welcome back to Algebra. Algebra 1, I suppose. So today's a really fun day. Today is really exciting. I hope I don't mess it up. Today is really fun. Because we're gonna witness the simplicity of A5. Now, witnessing it won't be so simple, but we have all the sort of ideas necessary for getting there. And so today that will be my goal, is to convince you that A5 is a simple group. It has no normal subgroups, interesting normal subgroups. Recall that simple just meant no non-trivial normal subgroups. Now, Kappa, regular participant here, informed me that in French, the name for normal subgroups is distinguished subgroup. Much better name, I would say. But anyway, so A5 is one of these non-collapsible groups, like atomic in some sense. Okay. All right, so let's begin with that. I should also announce that today in office hours is at 5. I will be doing some important stuff. I'll be, for example, trying to bootstrap and show that AN is simple for n greater than or equal to 5. So a much more general result. So that's an important office hours. I encourage my students to come to office hours, especially those who are struggling with group theory, which there are some now. So just something to think about. Okay. So let's do this. So the first thing I have are 2 basic observations. I want to do 2 basic observations. So observation number 1. This is really simple, really quite obvious, that a normal subgroup inside of a group is the union of conjugacy classes, is a union. This is clear. This is absolutely clear because of the definition. This is just by the definition. Whenever an element is in the normal subgroup, every conjugate of it has to again be in the normal subgroup. So its whole conjugacy class has to be a subset of the normal subgroup. So the normal subgroup is a union of conjugacy classes. Simple observation. Okay, observation 2 is a little bit, I mean, I haven't talked about it much, but it's also quite simple if you think about it. All right, so it's an H and a K setting. All right, so you suppose you have 2 subgroups. Of a group. Okay, so there's a simple relationship between 2 types of cosets. Okay, so you can look at the cosets. Whenever we write this slash and nobody said anything about normality, your default assumption is that we're just talking about the set of left cosets. Okay? So this is just the set of left cosets. And the set of these left cosets of the intersection inside the group H, this thing naturally injects the natural injection into these cosets. Left coset. So let me tell you the name of this map. Between a conjugate and a complement. Very different. Okay, good. So here we go. So what's the map? Here's the map. The map is this. Suppose you have a left coset. Here A is an element in H. A left coset of this intersection in capital H, you send it to the same left coset. Okay? Now, class. By now you should worry whenever someone defines a map like this. You have to worry, class. Verify that this is well defined. Okay, so you have to verify that this is an actual function, well-defined function. Okay, but once you do that, you'll see that this function, where you take a left coset and then look at this representative of the left coset and just tack on the left coset of K. This map is injective. Checking injectivity is easy. I'll do that. We'll meet in the middle. I'll check injectivity. If A times K equals B times K, where A and B are assumed to be in H, because I'm pretending that I started with two left cosets in H of the intersection, so I can assume A and B are in H. If you have this situation, then of course, B inverse A is in K. Right? That's just immediately following from here. Okay? And so, but B inverse A is also in H. Because A and B are assumed to be in H. And so B inverse A is in the intersection. And therefore, A times this coset equals B times this A times the A coset equals the B coset of this group. This is injectivity. Okay? So it's an interesting it's just a simple observation that when you look at these left cosets, they naturally inject into the set of these left cosets. Okay? Oh, suspicious? Oh, why are you suspicious? Okay. Alright. Okay. So, in particular, this index, if the indexes are finite, in particular this index, yes, you can no, because I'm not assuming K is a subgroup of H. Yeah. Think about the most general situation where H and K overlap but have separate parts. You know? Venn diagram. Just choose the most general Venn diagram. It's applicable even in that setting. All right. So one thing I want to point out is that this index, meaning the size of this group, the size of this left coset set is strictly smaller, or no, smaller than or equal to this index. So notice that we have this relationship between this inequality between the indexes. All right. Great. So that's the second observation. You get this inequality. All right. So I collected 2 observations, and we will use them next. I will use the second one next. So let's look at item number 2 for today's lecture. Let's try to understand conjugacy classes in the alternating groups. Okay, so this will be gnarly. All right. How do conjugacy classes in AN and SN sort of compare? So I want to review the conjugacy classes in SN. So this was last office hours. The conjugacy classes in SN are in just bijection with the cycle types. Okay? And the way we witness this is we actually know how conjugation works in SN. So imagine you have, let me do this example again. Let me do an example. Imagine you have one permutation, like 1, 2, 3, 4, 5, whatever, some permutation. And then suppose tau is another one. 2, 3, 7, 1, 4, 1, 2, 3, 4, 5, 5, whatever. Okay? Then sigma tau sigma inverse, the conjugation of tau by sigma, is in words, it is apply sigma, the permutation sigma, to the symbols in tau. And you get a new permutation. So let's do that. Look at tau. It's got a bunch of symbols in it. Apply sigma to each symbol. So what is sigma output for the number 2? We'll go one at a time. What happens to 2? 2 becomes 3. Okay. What happens to 3? 3 becomes 1. What happens to the symbol 7? 7 stays 7. What happens to 1? 1 becomes 2. What happens to 4? 4 becomes 5. What happens to 5? 5 becomes 4. Okay? All right, so conjugation in symmetric group is given by this formula. This is the handy dandy formula. All right, great. And so now it's quite easy to see that any 2 permutations that have the same cycle type are conjugate in SN. Okay. Great. So now the problem is the following. So now, what if we only look inside of AN? Well, first of all, one observation. So what's the issue? So pick an element in AN. Pick an even permutation. And let's just zero in on what the situation is. So the conjugacy class, and I'm gonna now I'm gonna emphasize the conjugacy class within this subgroup of sigma. It's the set of all conjugates by even permutations. This thing is a subset. It's a subset of the conjugacy class by the whole group. Because look, I can conjugate by more in Sn than I have available in An. So there's an obvious inclusion this way. Okay, so that's the first thing to notice. But what I also want you to see is that this conjugacy class is still a subset of An, thanks to the normality of An. An is normal because it is index 2. Okay, it's normal in Sn. Okay, so when you look at a conjugacy class in An, it will be contained in a conjugacy class of Sn. And actually, there are exactly two cases. There are two cases. Either the two conjugacy classes are equal, or the bigger this thing is twice as big as the conjugacy class for An. It's actually the union of two conjugacy classes. So in some sense, in a sense, this is either an inclusion or index 2. It's either equality or index 2. So how do you see something like this? How do you know that there are these two cases? The ultimate answer is just orbit stabilizer. So ultimately, this dichotomy comes down to orbit stabilizer. So let me state a theorem, which is an orbit stabilizer type theorem, okay? Fundamentally. So here's a theorem. Okay. So, suppose sigma is an element in An. Then, the two conjugacy classes are equal if and only if, so bear with me, these are equal if and only if the centralizer of this element, the set of permutations in Sn which commute with it, the centralizer of this element is not contained inside of An. Okay, these are the conjugacy class in An is the same as the conjugacy class in Sn exactly when this happens. And let me say this in another way. And this is if and only if The second if and only if is obvious. It's just a translation. If and only if there is an odd permutation which commutes with sigma. So this theorem is a criterion for knowing when a conjugacy class survives, or so when a conjugacy class for Sn survives as a conjugacy class in An, or if this doesn't happen, it splits into two different conjugacy classes. Okay, so let's see how you prove this theorem. So the proof sketch. Okay, so we're just gonna count elements, all right, and use orbit stabilizer. Okay, so what is conjugacy? This is just the orbit under conjugation action. That's obvious. What is centralizer subgroup? This is the stabilizer. Great. All right, so we're just reinterpreting these little pieces as orbit and stabilizer for some action. Okay. So the conjugacy, the number of elements in this conjugacy class is simply the size of Sn divided by the size of the centralizer. Okay, good. Let's write down the size of the other conjugacy class, the conjugacy class inside of An. On other hand, the conjugacy class in An of sigma, the number of elements it has, is, for the same exact reason, it is the size of An divided by the stabilizer in An when you conjugate, when you look at the conjugation action. But what is that? That's just this stabilizer intersect An. So these are the two numbers, and we're gonna see exactly when these two numbers are equal. Okay. These two numbers are equal precisely when this subgroup is not contained entirely within An. Reason. And I want you to witness it for yourself. The reason is observation number 2. Observation number 2 applied to H equals, let's say, H equals An, K equals this thing, G equals Sn. Kappa, well, I don't know why I did that, but I hope that you can just forgive me with these things. Those are not important. Well, actually, conjugacy classes are not groups, so this is fine. This is the appropriate use of number. I don't know which one you're talking about, but it doesn't matter. Like, that's not important. Okay, so use observation number 2, class, to see why the two numbers are equal precisely when this inclusion doesn't hold. Okay, that's the point. The point is simply that when there is a when this inclusion doesn't hold, then this index this is the same as saying that this index. Sorry. This is the same as saying the index Oh, did I might have swapped these. Maybe swap. That the index is 2, is exactly 2. So I'm spelling it out too much, so students go check this out. You'll get that this fraction equals this fraction precisely when you know that the index of this thing in there is exactly 2. It's you cancel out 2's in the 2 fractions. That's the point of it. All right. So the two conjugacy classes will have the same size when this index is exactly 2, thanks to observation number 2. Right, and that's why you get this first if and only if condition, just by checking sizes. Now, this if and only if is just translation. It's just a translation into other words. All right, so what's the summary? The summary is, if you want to know whether a conjugacy class in Sn survives as one conjugacy class in An, what you need to hunt for is an odd permutation that commutes with your sigma. All right? That's what you need to. If you start with start with an element in An and you want to know whether its Sn conjugacy class is the same as the An conjugacy class, as opposed to 2 separate orbits, 2 because the index of An in Sn is 2, you have to check this condition. Okay, so now we'll tease out what that condition means. So what does it mean for a sigma in An, an even permutation, to have an odd tau such that tau sigma tau inverse equals sigma, meaning such that tau and sigma commute? So what does this mean? So what it means, I need to get this straight in my head, hold on. It means the following. In sigma's cycle type, if you look at sigma's cycle type, it either has a cycle of even length or 2, it has 2 cycles of the same length. Okay, so this is I'm now further translating the existence of an odd permutation that commutes with sigma with, well, you'll have two cases. You'll either have you'll have one or the other. Okay, so let's check this. Let's check this situation. Okay, a cycle of even length. I'm just gonna check these. So suppose you have a cycle of even length, and I'll just pretend it's the first part of the cycle notation. The individual cycles in a cycle notation, they commute with each other because they don't share any symbols. So we can just pretend that it's the first one is like 1, 2, 3, 4, 5, 6, and then ends with an even number. All right, a cycle of even length, and then the rest. Okay, suppose you have an even permutation that's like this. All right. Well, confusingly, look at tau, which is this permutation. This part. Then tau and sigma commute, but tau is odd. All right, tau can be written as an odd number of transpositions. Go ahead and do that if you haven't tried that before. All right, so cycles of length that are odd, like 3 cycles, 5 cycles, those are even permutations. And cycles which have length even, like a simple transposition or a 4 cycle, those are all odd permutations. Okay, so this is an odd permutation that commutes with sigma. This is quite easy to check. All right, so that's this case. Now, if you have 2 cycles of the same length, for example, what should I call it? I mean, I'll just give symbol. I'll just pretend it's 1 through 5, 6, whatever. And same length, and we can assume that the lengths are odd, because if we had even ones, we'd be in the previous case. Okay, so we can assume they're odd. So like, for example, 8, 9. Okay. So these have the same length. They're both length 7. So suppose sigma was this and then the rest. Okay? Then here is an odd permutation which commutes with sigma. Now, 1 and 8, swap 2 and 9, swap 3 and 10, and then 7 and 14. This cycle, this transposition, this permutation is a product of odd number of transpositions. This is odd. But tau sigma, tau inverse is sigma. Okay? How do you do this quickly? Use the handy dandy conjugation formula, except I've now reversed the roles of sigma and tau. So just focus on this thing. What does conjugation by tau do? I mean, it will pick up this whole chunk and it will put it first. And it'll take this chunk and it'll put it second, the conjugation. So that's the same element, sigma. All right, awesome. So the existence of a odd permutation that commutes with sigma can actually be translated into these two cases. All right. So as an exercise, I'm going to ask you to prove the half that I haven't shown, which is, so what I showed is if you're in these two cases, then there is an odd permutation that commutes with sigma. But what you want to do next is argue the other way. If there's an odd permutation that commutes with sigma, then you have to be in one of these two situations. So what we want to glean from this is a simple criterion for now. That what we should check for in order to see if a conjugacy class survives in AN or not, or splits into two, check if you're in this situation or not in this situation. This is a criterion for non-splitting of the conjugacy class under Sn. Okay, so it stays as one orbit rather than splitting up into two orbits if you're in one of these two situations. Great. So now we're going to apply this to A5. Let's look at conjugacy classes in A5. All right, let's write some elements down. Let's write an element of the form ABC, and then D and E are fixed. This is an even permutation because it's a 3 cycle, and 3 is the odd number. This is even. So what is the conjugacy class in AN of ABC? How big is it? Let's ask, how big is it? Well, this has 2 cycles which have the same length, namely D and E. So this number is equal to the size of the conjugacy class in Sn of the same element, which we can count. This is just the set of all 3 cycles. What we're saying here is that every 3 cycle in A5 is conjugate to every other 3 cycle in A5. All right, so how many of these are there? Well, we have to do some counting thing. So, okay, so here's how you count these. One way to count them is to choose the 2 elements that are fixed, the D and the E, and then you need to order A, B, and C cyclically, but there's only 2 different ways to do that. So this should give you 20. All right, so I'm just counting the number of 3 cycles in A5. And the number of 3 cycles in A5 forms, the 3 cycles in A5 form one conjugacy class. And I'm just figuring out that number. Oh, further, 1011. Thanks for subbing. You don't need to do that. Terrible financial decision. All right. Oh. Yes. Kappa, when you write cycle notation, Kappa, good question. Cycle notation means that you've written your permutation in cycles that are disjoint. Absolutely. So when I say cycle, when you write the cycle type, cycle notation of an element, you have to, they're disjoint cycles, always. All right. When you multiply two permutations, okay, the two permutations might, when you put them next to each other, suddenly the cycles overlap, but you have to then multiply to get it into cycle notation again. So, okay, anyway. So this is a conjugacy class that has 20 elements. Let's look at another type of element in A5. Okay, so that's one conjugacy class. Let's investigate another conjugacy class. How about the conjugacy class in A5 of this kind of element? Well, hold on. This cycle type has an even length cycle in it. So this is the same as the size of the conjugacy class in Sn. Instead of being half the size. Instead of this conjugacy class breaking up into two, it's the same because of the criterion of the theorem that we established in part 2. All right. So now we just need to count this conjugacy class. This is the set of all permutations of this type. Okay, so how do you count that? How do you count how many there are? Okay, first, there's one fixed point. There's one fixed symbol. So there's one fixed symbol. And then you have to pair the other two into pairs of 2. And there's 3 ways to do that. There's 4 choose 2 ways to pair them, but that's ordered. And we get to freely commute 2 cycles in a cycle type because they're disjoint, kappa. All right? So this is 4 choose 2 divided by 2. So this is 15. This conjugacy class has 15 elements. Okay? Notice I have to only consider even permutations. And that's clearly an even permutation. And so was this 3 cycle. Okay, so let's what's the other possibility? There's actually only one other possibility. Okay, so let's look at a cycle that's a 5 cycle. Okay, how big is the conjugacy class in AN of a 5 cycle? In A5 of this 5 cycle. Okay. Well, this is not in those 2 criteria. And so this thing actually splits into the sum. Sorry. This thing is half the size of the conjugacy class in Sn. This is strict. I'm going to put a 1/2 here. 1/2, the orbit is half as small, is half the size as the conjugacy class if we were allowed to conjugate by everything in S5 rather than only even permutations. Okay? All right, so this conjugacy class splits into 2. Now, how big is this one? This is just the set of all 5 cycles. And you can count this. You can count this using orbit stabilizer. It's like counting certain kinds of necklaces, if you think about it. So how many 5 cycles are there? There's actually 5. I'll write it as if it's an orbit stabilizer problem, and I'll let you piece together the orbit, the action, and the stabilizer and the orbit. Okay, so this is 5 factorial over 5. Okay, S5 acts on the set of 5 cycles by just permuting the symbols. But a given 5 cycle has a stabilizer of size 5. I want you to find it. Okay, so this is 24. And so this conjugacy class is size 12. All right. So let me sort of show you what's going on. For example, the conjugacy class in A5 of the symbol of the element 1, 2, 3, 4, 5 is a 12 element set. And then if you look at the conjugacy class in A5 of 2, 1, 3, 4, 5, notice what I did. To go from this element to this element, I conjugated by an odd element. Which is odd. But if you take the disjoint union of these two conjugacy classes, you get the conjugacy class in S5 of the original element. All right, so this is what's happening. Either you get one preserved conjugacy class, or it splits into two. Okay, so you get 12 and another 12. So you get 12 and then another 12. So let's just do a sanity check. I know I'm over time. I'll just watch the video later after all your other classes. Okay, so I'm just gonna do a sanity check in this conjugacy class calculation. Okay, look. We accounted for 20 elements like this. We got 15 like that, so that's 35 so far. And then we got 12 plus 12, which is 59. 59 elements have been accounted for. There's one more. Oh, there's one more conjugacy class. Okay, this is just one. Okay, so we know how big every conjugacy class in A5 is. There's one of size 20, there's one of size 15, there are two of size 12, which the 5 cycles break up into 2 types. And then there's one of size 1. Okay, so now the conclusion, the grand conclusion. A5 is simple. Okay? Why? Okay, so you need to construct a subgroup which is a union of conjugacy classes. Of conjugacy classes. Okay, that's the first observation. Okay, we know one extra thing. You have to include this conjugacy class. You must include the identity conjugacy class, because the identity is an element in your fantastical normal subgroup that you think is there. Must include the conjugacy class of the identity. So you have to write 1 plus 12s, maybe some 12, maybe 12, maybe another 12. You get to choose. Just try this. Maybe a 20. Maybe 15 plus, and plus maybe 20. Okay, you get to choose how to add these numbers to produce the order of a subgroup. Needs to be some number dividing 60. Some number less than 60 dividing 60. And there are no combinations that work. No shot. All right? So it's impossible to construct a normal subgroup of A5 because we figured out all the sizes of every conjugacy class, and you couldn't put those Legos together, including the trivial conjugacy class. There was no way to put them together to even satisfy Lagrange's theorem. So that's why A5 is simple. And now the question remains, how the heck do I know that AN is simple for n bigger than or equal to 5? Am I gonna do a conjugacy class type? This is like a case check, really. Am I gonna check the sizes of conjugacy classes? That seems like a combinatorial nightmare. So there's another route. In fact, there are like, I don't know, hundreds of routes to witnessing the simplicity of AN for n bigger than or equal to 5. There are, I don't know, many other ways. And that's what I'm going to sketch during office hours. We'll collect some other neat facts about alternating groups that will help us prove the much more general statement that AN is a simple group for all n bigger than or equal to 5. The last thing I want to say, just to make sure you understand, A4 is not simple. It contains the line 4 group as a normal subgroup. Okay, so A4 is not simple. A3 is simple, but it's like too simple. It's too simple. I mean, it's just Z mod 3Z. So, you know, which alternating groups are simple? Okay. Technically, A3 is simple. And then A5 and beyond. And A4 is not simple. Okay. But A3 is like a cyclic group of order prime, so it's kind of not very scary, and abelian and so on. So just remember that technically A3 is also simple, but it's very, very easy group to understand. Okay, good. So office hours will be extra exciting. I will try to get through the proof that AN is simple for all n greater than or equal to 5. And we'll have to learn interesting facts about AN, like you learn that simple transpositions generate SN. Are there similar statements for AN? Certain types of permutations generating AN? And yes, there's a ton of these kinds of statements, and we'll try to collect a couple. Enough so that we can navigate through the proof of simplicity of AN for n greater than or equal to 5. Okay, so many questions. All right. Okay, Dr. Young's lab, awesome. Good to see you. So, Kappa, what are your questions? What's the question? Oh, Gath! Hello, Gath. Good to see you. Hope you've been having a good semester. And hope Hope your students are appreciating your crazy, awesomely designed organic chemistry class. If a set is the orbit of someone under an action, isn't that set a cyclic group? No. Next question. Everything, okay, Kappa, everything is a cyclic group if you squint at it. Everything is a cyclic group. So orbits are just subsets. They don't have the structure of a group necessarily. Now, when your group, so every set can be witnessed as a cyclic group. All right, look, Kappa, look. Look, here's a set. Here's a set. Wow, incredible set. I'm gonna say that this set is Z mod. Hold on. Oh, Kappa. Actually, you were looking at Z mod 17Z. But who cares? The structure that you put on this set has no relationship with the orbit action or the other group that was acting, and this was the orbit. It has you want your structures to be compatible with each other in some sense. So if you just randomly place a group structure on a set, there's no reason why that group structure has anything to do with your previous math problem or your previous setting. So orbits? So Kappa, here's what you can say about an orbit. An orbit, okay? An orbit doesn't inherit the structure of the group. What an orbit inherits is simply an action of the group. An orbit inherits an action. Naturally, from the context that it came up in. Inherits an action of a group, but not the group structure itself. However, if the stabilizer of a point is normal, then the orbit inherits the structure of G mod H. And G mod H need not be a cyclic group. It could be any group. So there is something Kappa here, but it's in general, an orbit is just an orbit, meaning a group acts transitively on it, and you can't push the group structure onto the orbit the way you want to, the way that is in your mind, which I can see in your mind. That's not going to produce a well-defined group structure. It will only produce it if the stabilizer of a point is normal. Okay. Yeah. Let me go through it again. Let me go through it, Kappa. It's good. It's good. It's important to get this logic. Okay. So statement one. A normal subgroup is the union of conjugacy classes. Statement 2. Lagrange's theorem. Order of a subgroup divides the order of a group. Any kind of subgroup. Okay, so this is 60 for us. Okay. Okay, statement 3. Here is the list of all conjugacy classes. There are 5 conjugacy classes. One has size 20. Another one has size 15. A third one has size 12. And a fourth one has size 12. Oh, and a 0th one has size 1. Okay, so here are your options for combining conjugacy classes in order to try to produce a subgroup of A5. Here are your options for the sizes. So you have to include this, must include this, because identity is in any subgroup. So you have to add 1 with some, you get to choose these. Yeah, you have to pick 0 because the identity element is in your subgroup, your fictitious subgroup. Let's give it a name. So we know that identity is in here. So the whole conjugacy class of identity is in there, obviously. Okay, but every time you choose an element in N, the whole conjugacy class has to get into that subgroup. But now you see, you can't do it. Like, maybe you chose 20. What are you gonna do to get to some number that divides 60? Yeah. It's actually not, it's a great argument. And you have to double check it carefully. Yeah. So, but yes, but this kind of playing around with how big the conjugacy classes are, it's gonna be a nightmare to try to prove in the case of even like A6. Why is A6 simple? We're gonna have to develop some other tricks, folks. Much more subtle arguments. Yeah. Yeah. Oh, hello, Ann Burrows. How's it going? Thanks for lurking. Good to see you. Another chemistry luminary. Great scholar of chemistry. I learned about N. Burrows from my time in Gath's stream. I hope I got that history right. Hey. Oh, Algebraically Challenged is here. Lots of celebrities are here. Okay, awesome. Awesome. So we have our first crazy group, A5. It's if there's a periodic table of elements, if there's a periodic table of groups, finite groups, we have just witnessed one of the strangest entries. It's like the discovery of like uranium or something. Like, wait. Oh no, there's some weird big atoms out there. A5 is your first example. Cyclic groups of order P. Come on. What's there to say about them? Okay, now A5, first example. Oh yeah, class, here's something. A5 is the smallest non-cyclic simple group. This statement is a tour de force of all the techniques we'll ever learn. I'll do this in class or office hours at some point, just to like pull all the levers that everything we have, we throw at it. We'll be able to see that if you have a simple group that's not cyclic, not a prime Zmod PZ, then it has to have 60 elements or more. So that's just a lot of group theory, all packed together. So we'll try to do that. Yes, uranium. A5 is like the uranium of... Yes, Kappa, yes. Every time some two non-trivial normal subgroups. Oh yeah, the chat is a crazy group too. I actually never thought of that. Yes, the chat is a crazy group. Actually, the chat has 18 elements in it, according to my metric here. So, yeah, it's there are some good possibilities for what the chat is, but definitely not simple. It is... Chat contains normal folks in it. Wow, what a terrible... what a terrible joke. Okay, folks, I have to go and learn something about Taylor polynomial. Yeah, right, okay, yeah. I have to go learn about Taylor polynomials. Tropical Geek is waiting for their daily dose of shungite. Here you go. Let the 5G not harm you. Let this protect you. And that's all the redeem. Okay, thank you, proper for following. Thanks, Self. Life. Thanks. Okay, thanks, Further. What the heck are you thinking, Further? Why'd you sub? Thank you, Mystic. Thank you, Infinite. Thank you, whatever. Yeah. Each and every one of you. All right. Great. Okay, let's get out of here. Let me cram. What are we doing? Well, we're leaving now. We're leaving. Mr. Patel, we're leaving. You came at the worst time. All right? Wake up early and come to class. The usual time. All right? Press the follow button. You'll be notified when class starts. All right, Mr. Patel? Classic Patel. You know, classic Patel behavior. All right? Yeah, I can say that for reasons that I won't disclose. All right, awesome. Yeah, Indian Standard Time, but Gujarati Standard Time. Okay? Classic Patel. Jeez. All right. Get out of here. I'm just gonna shake my screen. Wow. Ooh, emergency. Emergency. Oh, I have to get out of here, folks. Wow. Yeah. Okay. There's my excuse for leaving. All right. End the stream.